Well, thanks a lot, Kara, for organizing. It's really nice to be here. And I'm happy to present this study that's been published a couple months ago. But it's been a long time in review, so at different journals. So I'm very happy that this is out, and I hope you're also interested. So this is on an emergent constraint on future ocean heat uptake. And the motivation for this work is, as most of you probably know, that the ocean stores most of the excess energy that's being stored in the climate system in the form of heat, which is a good thing because it's not warming the atmosphere. But it's also a negative thing because ocean warming has consequences for marine ecosystems, extreme events, etc. And this warming is present globally, but it's most pronounced in the Southern Ocean and Atlantic, where the ocean circulation makes the ocean more efficient at taking up heat from the atmosphere. So when you look at this ocean heat uptake in a globally integrated sense, this is what climate models simulate over the historical period and into the 21st century for global ocean heat content. You can see that there's a big spread in model predictions. So relative to the year 2024, which is when I made this plot, I guess, there's a big spread by the end of the century in the range of ocean heat uptake that climate models predict. So this, of course, depends on the emission scenario you look at, but even for the same emissions, models vary wildly in their predictions. And right, so these are the different scenarios. And this directly translates to negative consequences associated with ocean heat uptake. So for example, the second y-axis here shows the thermal expansion of the global ocean due to ocean heat uptake, which is practically proportional to ocean heat uptake. So it's really important to constrain this, this range if you want to be able to make decisions on future impacts of ocean heat uptake. So the question we ask here is, are we able to find some kind of process understanding that will help us to reduce this uncertainty? Because right now, all we have is these raw model projections, and we don't know which one is right, which one is wrong. So what previous studies have done to address this is to look at past trends in ocean warming. So this is a figure from a study by Liu et al. 2021. And essentially what they're showing is that, so each dot here is a different climate model. And the x-axis is the past trend in ocean heat uptakes over the past 2 decades. And the y-axis is the future ocean heat uptake. And what they try to show is that models that have a stronger trend in the past will also have a stronger uptake in the future. So, of course, you could argue that this relationship is not perfectly linear, but what they concluded is that since most models overestimate the past trend, because they're to the right of this observation line, then they should also overestimate the future heat uptake. And so as the conclusion was that, okay, probably ocean heat uptake will be smaller than what the models, the raw model projections predict because of this relationship between the past and the future. However, we think that this kind of approach can be sensitive to internal variability. So if you look at the x-axis, this is a trend over 14 years. And we know that the recent climate has been subject to substantial internal variability that can temporarily shift or change trends in one direction or the other. And also this neglects a possible regime shift in the climate system. So if something fundamentally changes in the way that the ocean takes up heat, then the past behavior would not be indicative of the future behavior. So therefore, in this study, we proposed a new constraint to reduce the uncertainty in future ocean heat uptake, which is based on Antarctic sea ice. So why Antarctic sea ice? essentially, we found this surprising result that when you compare simply the historical sea ice extent in the Antarctic in different climate models with their future globally integrated heat uptake, you have a very strong relationship, so a correlation of almost 0.9. And this is pretty surprising because the global ocean heat uptake is a globally integrated quantity that happens everywhere at once, whereas the Antarctic sea ice extent is really a localized quantity in the climate. So yeah, the high correlation is quite surprising. So we asked, why is this the case? Is this just a statistical chance? So our initial hypothesis was that maybe models that have more sea ice, when the ice melts, this opens up more of the ocean area, which can then take up heat. So maybe it's just about the local effect of the sea ice melting, and then the ocean with the albedo feedback becomes more subject to heat uptake. But when you think about it more precisely, or when you calculate it, you'll see that the area of the sea ice that's present and that can melt is just way too small to account for these numbers of heat uptake globally. So therefore, another mechanism must be at play to explain this relationship between sea ice extent and ocean heat uptake. So the one thing we found is that the sea ice extent is related in a broad sense to the base state climate. So here on this plot, I'm showing the correlation across different climate models between the sea ice extent in the Antarctic and the temperature of the water. So this is zonal mean, latitude and depth. And the blue colors indicate that climate models with more sea ice have colder water at these locations. So of course, in the Southern Ocean at the surface, colder water translates to more sea ice, which is fully expected. But you can also see that this signal goes all the way through the global ocean to the north at these intermediate depths along isopycnals, because this is the water that's being upwelled by the overturning circulation in the Southern Ocean. So actually, the sea ice is not only a very local thing around the Antarctic, but also connected to very broad global ocean features. And a similar thing is found for the atmosphere, where models with more sea ice also have thicker or more cloud cover across the Southern Ocean mid-latitudes, which is shown in the red color here. Okay, so the sea ice is related to the base state climate, but it's also related to future climate changes globally. So the models that have a larger sea ice extent initially, this correlates also with stronger surface air temperature warming in the Southern Hemisphere, as shown on this panel. It translates to stronger ocean warming, the SST, and to a stronger global cloud feedback parameter. So this is still quite striking because like I said before, the sea ice is so relatively small that it has an outsized impact on the global cloud feedback parameter. So the mechanism we propose to be responsible for these relationships is that if you consider the initial state of the Southern Hemisphere, so you have the sea ice, the clouds, the cold, relatively cold ocean, as you go from the historical past to the future under climate change, you enter a perturbed state where the low cloud cover is reduced, letting in more heat. The sea ice is melted. The surface air temperature is as the surface water temperature is warmer, and you have excess heat uptake into the ocean. And essentially, the amplitude of this transition, of this climate change, depends on where this initial state is. So this is symbolized here. So if you start from a cold state that has a lot of sea ice, a lot of cold water, a lot of clouds, and you go to a warm state in the future, you will have a large transition. So more sea ice is lost simply because there was more present at the start, but you will also have more warming, stronger cloud feedback, and a lot of ocean heat uptake. On the other hand, if you start from a relatively mild state where the ocean is already kind of warm and there's not that much sea ice in a particular climate model, and then you go to the future warm state, then the transition will be smaller. So less sea ice will be lost, and ultimately less ocean heat uptake will occur. And this mechanism can be seen when you look at how the cloud feedback, the surface warming evolves over the 21st century. So here on this plot, I'm showing again, it's an intermodal correlation of the sea ice extent in the Antarctic initially with local surface warming. And here in the 1980s, it's all stippled, so there's no correlation. But as you go to future decades, so this is the 2000s, you see that a signal emerges in the Southern Ocean where more initial sea ice translates to stronger warming in these regions. And then as you go to the 2020s, this signal already covers most of the Southern Hemisphere. And by the end of the century, in 2090, there's a very strong correlation of a lot of initial sea ice translates to strong warming in these locations. And really, if you look at an animation, you can really see it spreading from the Southern Ocean to cover the global ocean. So now this allows us to do a similar thing as this previous study did, which is to take this relationship that we found initially, that we have now explained through a mechanism, and simply add on the observations that we have of historical sea ice extent. So over this period, we've had satellites measuring sea ice concentration, so we know what the approximate sea ice extent is. So this is in Southern Hemisphere summer, I should say, plus and minus some uncertainty that's conservatively estimated. And just looking at this plot, you can see that most of the models underestimate the historical sea ice extent. And according to this relationship, they should also underestimate the future ocean heat uptake. So if you do the calculation of what the heat uptake should look like, you find that the central estimate of end of century global integrated heat uptake is 14% higher than simply taking the raw climate model outputs. And you can also see that the uncertainty range is reduced by about a third. So this is under the SSP 585 scenario, which is quite strong, but it works under all SSP scenarios with differing details in the exact values. And the same, so this is showing the same thing as a box plot, where you have the prior distribution of ocean heat uptake just from the climate model output in gray, which has a median that's relatively low in white. And then after you apply the constraint, the new central estimate and uncertainty is shown in red, where you can see that there's a definite upward correction of 14%, as I showed, and a reduction of the uncertainties. But the same thing can also be done for surface warming, because exactly the same mechanism is not only responsible for ocean heat uptake, but it's also involved with surface warming generally, as I've shown on this northward propagation. So we also find a 3% upward correction of global surface warming with a slight reduction in uncertainty, and an upward correction in the global mean cloud feedback parameter, which we're able to constrain with exactly the same approach. Now to test the robustness of this constraint, we first of all can consider that the sea ice extent in the models, which is shown here in these gray lines, is consistently, on average, consistently underestimates the true observation values of sea ice extent. So all these color lines are observations and different reconstructions going back for centuries. But you can see that the ensemble mean is always an underestimate. So that's no matter what time period you choose or what phase of internal variability you're in over this past, the general direction is always the same. The models are simply too warm and don't have enough sea ice in the Southern Ocean. And we also tested a bunch of other things. So instead of using summer sea ice, we can also use annual mean or winter sea ice. And the qualitative correction is still the same. Same thing for the time period. So the sensitivity to internal variability is not sensitive. It doesn't really matter which of these observational sources you choose because they're all very similar compared to the huge intermodal spread, as you can see. And it even works in an out-of-sample test with CMIP5 models instead of CMIP6. So the same thing is valid there. So I'm already going to conclude. So we exploited this pre-industrial coupling between sea ice, the clouds in the Southern Ocean, and the global deep ocean, which is characteristic of the baseline state of the global climate in models. And we find that this baseline climate state preconditions the future amplitude of warming and ocean heat uptake via this northward spreading cloud feedback. And our emergent constraint, when you do the calculations, gives an upward correction of around 14% in the central estimate of global ocean heat uptake. And this is, in particular, it's bigger than what was previously assessed. And we believe that our constraint is less sensitive to variability in past trends than other studies that have attempted to do the same. So this is it, and I'm happy to take any questions.